It's 1:23 in the morning inside the control room at Chernobyl Unit 4. The reactor has been unstable for hours. Power is low, too low. Most of the control rods have already been pulled out to keep the reaction alive. The test is almost finished, and everyone in the room wants it over. Then the shift supervisor gives the order. An operator reaches for the one button every nuclear plant on Earth is designed around, a Z5, the emergency shutdown, the final safety system. The button that is supposed to stop the reactor instantly. He presses it, and in the next few seconds, reactor power doesn't fall, it explodes upward. So here's the question that should be keeping you up at night. How does the emergency stop become the trigger? To understand what went wrong, you first need to understand something terrifying about nuclear reactors. Once fission starts, it does not naturally want to stop. Think of a fire throwing sparks into dry grass. One spark starts another fire. That fire throws more sparks. Those sparks start even more fires. Nuclear fission works the same way. A uranium atom splits and releases neutrons. Those neutrons hit more uranium atoms, splitting them too, which releases more neutrons, which split more atoms. And the whole chain keeps feeding itself. That chain reaction creates heat. The heat boils water into steam. The steam drives turbines and generates electricity. That's the useful part. The dangerous part is what happens if the reaction speeds up faster than the cooling system can control it. More heat creates more steam. More steam reduces cooling efficiency. Less cooling creates even more heat. The loop tightens on itself. Engineers call this thermal runaway. It's like turning up the burner under a pressure cooker while simultaneously sealing the lid tighter shut. Eventually, the pressure stops being manageable. So every reactor on Earth has an emergency shutdown system designed for one job: kill the chain reaction immediately. That system is called SCRAM, Safety Control Rod Axeman, a name dating back to the world's first nuclear reactor in the 1940s. And the way SCRAM works is surprisingly physical. Inside the reactor are long control rods made from neutron-absorbing materials like boron carbide. Boron is incredibly good at capturing neutrons. Think of it like a catcher's mitt for atomic particles. A neutron flies in. The boron catches it, and that neutron is removed from the chain reaction completely. No neutrons means no fission. No fission means the reactor power drops. In most modern reactors, these rods are suspended above the core using electromagnets. The instant power cuts, gravity pulls the rods straight down into the reactor. No software, no operator timing, just physics doing the work. And usually, it works beautifully. But the RBMK reactor used at Chernobyl had a hidden flaw buried inside the rods themselves. A flaw Soviet engineers already knew about years before the disaster. And that flaw turned the emergency shutdown into the exact thing it was supposed to prevent. What makes this story genuinely disturbing is that the reactor did exactly what its geometry told it to do. Not what the operators expected, not what the safety manual promised. The shape of the rods themselves contained the failure. And to understand why, you need to understand two materials that look almost identical, but behave completely opposite inside a nuclear reactor. This is where the entire disaster flips upside down. Because inside a reactor, there are two ways to affect neutrons. You can absorb them, or you can slow them down. And those two things sound similar, but they do completely opposite jobs. Boron carbide absorbs neutrons. It removes them from the reaction entirely. Graphite does something different. Graphite moderates neutrons, meaning it slows them down. And here's the counterintuitive part. Slower neutrons are actually better at splitting uranium atoms, which means graphite can increase reactor power. Same neutron, different speed, more fission, more heat, more energy. So now picture the RBMK control rod itself. Most of the rod was boron carbide, the absorber. But the bottom section of every rod contains something else: graphite. About 1.25 meters of it. And that detail changed everything. Because when operators pulled the rods upward during operation, those graphite tips stayed inside the lower part of the reactor core, displacing water. That matters because in the RBMK design, water wasn't just coolant, It also absorbed neutrons. So replacing water with graphite quietly increased reactivity in parts of the core. Now here's the fatal sequence. When AZ-5 was pressed, all 211 rods began descending into the reactor. But the first thing entering the core was not the boron absorber. It was the graphite tip. For the first few seconds of the shutdown, the reactor briefly received more moderation before it received absorption.
It's like a fire extinguisher spraying gasoline before the foam arrives. That effect has a name: the positive scram effect. The emergency shutdown initially increased reactor power instead of decreasing it, and under normal conditions, the reactor might still have survived that spike. But Chernobyl wasn't operating under normal conditions anymore. The reactor had been pushed into an unstable state. Power levels were dangerously low. Xenon poisoning had built up inside the core. Coolant water was beginning to boil, and the operating reactivity margin, the number of control rods still inserted for stability, had fallen to around 6 to 8 rods instead of the required 30. The reactor was already balancing on the edge. Then the graphite tips arrived. The RBMK rods moved at roughly 0.4 meters per second. The reactor core was 7 meters tall. Full insertion took around 18 seconds. That's an eternity inside a runaway nuclear reaction. In a modern Western pressurized water reactor, the kind used at plants like Vogtle in Georgia, shutdown happens in under 5 seconds, with neutron absorption beginning immediately from the first moment the rods move. No graphite, no delay, no power spike. But at Chernobyl, the graphite tips increased reactivity precisely when the reactor was least capable of surviving it. Power surged violently upward. Estimates suggest reactor output climbed to roughly 30,000 megawatts thermal, about 10 times the reactor's design limit. Fuel channels ruptured, water flashed instantly into steam. Pressure exploded upward through the reactor vessel, and then the entire 1,000-ton upper biological shield, the reactor lid itself, was blown into the air. Seconds later came the second explosion. Graphite inside the reactor ignited. Radioactive debris blasted across the facility, and the open reactor core began burning into the night sky. This wasn't a software glitch. It wasn't just operator error. It was a physical contradiction built directly into the geometry of the shutdown system itself. The very mechanism designed to stop the reactor briefly accelerated it instead. Every modern nuclear reactor carries the lesson of Chernobyl inside its safety systems. After the disaster, RBMK reactors were modified with faster emergency insertion systems and redesigned rod geometry that removed the graphite tip problem entirely. Because engineering doesn't just evolve through success, it evolves through failure, sometimes catastrophic failure. And the terrifying part is this: the AZ-5 button worked exactly as the reactor was designed to work. That design was the problem. The rod geometry was eventually fixed, but the RBMK still carried another dangerous flaw, something called the positive void coefficient, a second instability that made the reactor even more dangerous under low-power conditions. And that flaw is a whole story by itself. Subscribe, because that's the next breakdown.